In this video, I will be discussing about applications of differential equations. So far, we have only discussed the methods and techniques of how to solve an ordinary first-ordered differential equations. It is also very important to learn the different applications from both realms, the geometrical and the physical aspects of its use. Specifically, problems in geometry, physics, chemistry, civil engineering, electrical circuits, and the like will be considered here in our discussion. And one of the very common problem in mathematics is to determine the equation of a plane curve. Usually, in this problem, we are given the following: the slope function of the given curve, that is f of x and y. Now, this is just a slope function because the slope of the given curve may change at different values of x. So it is not a constant slope sometimes. In other words, the slope of the tangent line of the curve changes at different values of x. So it's not always a constant slope. So that is why you are given just a function of its slope. And also we are given the point x sub 0, y sub 0 at which the curve passes through. And we will use the idea that the slope of a function f of x at any point of its curve is the first derivative of the function. Or you may write the derivative of y with respect to x. So the slope of its tangent line is equal to the first derivative of the function with respect to x. And the slope of its normal line is just the negative reciprocal of the slope of its tangent line, because the normal line should be perpendicular to the tangent line. Now let's proceed to our example number 1. Find the equation of the curve passing through the point 3, negative 1, and has a slope of 2x over y at any of its point xy. So, in this problem, we are given that the slope of the curve is 2x over y. Then, we can say that the derivative of y with respect to x is equal to 2x over y. And you see that we have now our differential equation. And when we multiply both sides of the equation by y dx, we have y dy, which is equal to 2x dx here. And when we integrate both sides of the equation, so we have the integral of y dy is equal to the integral of 2x dx. And we know by the power rule that the integral of y is y squared over 2. And also this one is 2 times x squared over 2 plus the constant of integration, say c prime. And simplifying this equation, we have y squared over 2, which is equal to x squared plus c prime here. And multiplying both sides of the equation by 2 so that we can get rid of this 2 here in this denominator, we have y squared, which is equal to 2x squared plus 2c prime. And if you are going to subtract both sides of the equation by 2x squared, we have y squared minus 2x squared, which is equal to c, because 2c prime is just a constant. So we'll represent this 2c prime as just c. Then therefore, we have now the equation of the family of curves, but the particular curve which passes through 3, -1 is obtained by this equation of the family of curves, which is y squared minus 2x squared, which is equal to the constant c at the point 3, -1. And if you are going to substitute our y, which is -1 here, we have -1 quantity squared minus 2 times the square of our x, which is 3 here. So we have 2 times 9, which is equated to the constant c. So we have 1 minus 2 times 9, and 2 times 9 is 18. So therefore, our c is just equal to -17 here. Thus, our particular curve is equal to y squared minus 2x squared, which is equal to the c, which is -17. And if we are going to multiply both sides of the equation by -1, here, this -2x squared becomes positive. So 2x squared minus y squared, because this y squared becomes negative now. And this is equal to positive 17. Then therefore, this is the answer for this problem here. Now let's proceed to our example number 2. Determine the equation of the curve passing through the point 1, 0 and has a slope at any point xy equal to x squared minus y over x plus y squared. And since the slope of the curve is x squared minus y over x plus y squared, then we can formulate our differential equation, because we know that the slope is the first derivative dy dx here. So dy dx is equal to x squared minus y over x plus y squared. And multiplying both sides of the equation by the LCD of these two fractions, which is dx times x plus y squared, we have x plus y squared times dy. And this is equal to x squared minus y times dx here. And distributing this dy to this binomial, we have x dy plus y squared dy. And this is equal to x squared dx minus y dx. If you are going to distribute this dx to this binomial here, and moving these two terms here to the left side of the equation, we have x dy. So we have plus y dx plus y squared dy minus x squared dx, which is equal to 0. And you notice that this is an integrable combination, because this one is just the differential of the product of x and y. And this is added to y squared dy minus x squared dx. Then therefore, we can find the antiderivative of each term in this equation. So we have the integral of the differential of the product of x and y plus the integral of y squared dy minus the integral of x squared dx, which is equal to the integral of 0. And we know that the integral of the differential of the product of x and y is just xy, and the integral of y squared is y cubed over 3. And also the integral of x squared is x cubed over 3, which is equal to the constant of integration c prime. Then multiplying both sides of the equation by -3 so that we can eliminate this 3 in the denominators. Here we have -3xy minus y cubed plus x cubed, which is equal to the -3c prime. And rearranging the terms so that we can have the first term as x cubed, we have x cubed minus 3xy minus y cubed, which is equal to c, because -3c prime is just a constant. And now we have already the equation of the family of curves. But the particular curve which passes through the point 1, 0 is obtained by this equation, x cubed minus 3xy minus y cubed, which is equal to c at the point 1, 0. When you substitute our x and the y to this equation here, so we have 1 cubed minus 3 times 1 times 0 minus 0 cubed, which is equal to the constant of integration c. So we have 1 minus 0 minus 0, which is equal to c. Then therefore, our c is 1. Thus, our particular curve is x cubed minus 3xy minus y cubed, which is equal to 1. And this is our answer for this problem here. Now let's proceed to our example number 3. Find the equation of the curve such that the x-intercept of its tangent line at any point xy of the curve divided by the square of the ordinate of the point of tangency is a constant here. So if we will sketch the graph of this curve, the graph here is the blue curve and its tangent line here, which is the black straight line. The point of tangency is at this point x, y here, because it's given that the tangent line at any point xy. But if this is our tangent line, the tangent line intercepts the x-axis at the point x sub 1, 0. And we know that the slope of the tangent line is the derivative of the function y. So this is dy dx, which is equal to the difference of the two y's here. So we have y minus 0 over the difference of the two x's. So we have x minus x sub 1. And multiplying this equation by the LCD of the denominator, we have x minus x sub 1 times dx. So we have x minus x sub 1 times dy, and this is equal to y times dx. And distributing this dy to this binomial, we have x dy minus x sub 1 dy, and this is equal to y dx here. And isolating this term here, because this contains x sub 1, we have x dy minus y dx, which is equal to x sub 1 dy. Then dividing both sides of the equation by dy, we have x dy over dy, which is 1, minus y times dx over dy, which is equal to x sub 1. So this is now our equation 1. But we are also given from the condition in the problem that if we divide the x-intercept, which is x sub 1, by the square of the ordinate of the point of tangency, which is y, we have x sub 1 divided by y squared, and this quotient is a constant. So we set this equation as our second equation. So substituting equation 1 to equation 2, we have our equation 2, which is x sub 1 over y squared, which is a constant. We can substitute the value of x sub 1 from equation 1. So we have x minus y times dx over dy divided by y squared, which is equal to k. And if we multiply both sides of the equation by y squared, we have x minus y times dx over dy, which is equal to ky squared. Then moving these two terms to the right hand side of this equation, we have ky squared, which is subtracted by x, plus y times dx over dy, and this is equal to 0. And to get rid of this dy in this denominator, we multiply both sides of the equation by dy. So we have ky squared dy minus x dy plus y dx, which is equal to 0. Now rearranging the terms here, because this one is an integrable combination, we have y dx minus x dy, which is added to ky squared dy. And multiplying both sides of the equation by 1 over y squared, we have y dx minus x dy divided by y squared plus k dy, which is equal to 0. And we know that this is already a differential of a quotient, which is x over y, and this is added to k dy here. So integrating each term in this equation, we have the integral of the differential of x over y plus the integral of k dy, which is equal to the integral of 0. And we know that the integral of the differential is x over y here plus ky, which is equal to the constant of integration c, and multiplying both sides of the equation by y, so we have x plus ky squared which is equal to cy. Then therefore, this is our answer for this problem here. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.